es totalmente absurdo. En este momento digo que va a ser un papel de algo sin saber qué es. Sí, pues vamos a como que debilita a vosotros esto.
Seeing faster computers than this.
Is this based on solitons?
Yeah. I'll show what Turing was
Technology is not so mature.
Something wrong with it.
So, welcome everybody. Today's speaker doesn't need much of an introduction, so I need Damia to begin with the talk.
There is some problem with that. Like the bar is not as it used to look like, so something works. Okay, so thanks for coming, everybody. Well, today I put this title, Computing with Dissipative Solitons. But I'll be talking about not something else, but something, let's say, more general maybe. But I want to talk about this in complex systems. Usually we have is that, well, the most striking example is probably biology, that starting from the physics, the law of physics, you see emergent structures, very complex things, which are able to compute information. Okay? So that's a characteristic of complex systems. So I want to talk about that, how the emerging properties of complex systems allow to make some computations. Okay? Because here at the end, I will do that using these solitons. But before that, I want to, well, I've tried to make this presentation not so very general, so I hope you can all enjoy it. And I'll give a very simple example. Sorry? That's the example of a complex system. Static. So the first half of the talk I'll talk about the game of life, which is a game. So it's a cellular automata that John Conway and his group, this is from the 70s or something like that, we're trying to answer the question of which are the simplest rules where a self-reproducing thing can emerge, something like that. No? So they try to do this with the cellular automata, and they end up with these rules of the game of life that show through complexity. It's a very nice example that captures a very simple thing that captures this this idea of emergent structures, how these emergent structures can do things. Okay, so I'll go through the game of life a little bit, and then I'll go to the true system we have been working on. Sorry, I say not the authors, because this is mainly the work of Adrian on his thesis on dissipative solitons in nautical systems, and also with Gomila, of course. Okay, so before I go with that, well, the game of life. I don't know if you know it. This is from the 70s. It has a lot of success, a lot of people working on, and it reached the mainstream and so on. Essentially, well, the game of life, you have a grid. And then you have rules for the cells. The cells can be on and off, and then depending on these neighbors, the next time step you will get on and off. So, if it is populated, you have a populated cell. If in the neighbors, one or no neighbors, so each cell with one or no neighbors die of loneliness. Yeah. If it has 4 or more neighbors, it will also die of overpopulation. And it has 2 or 3 neighbors survive. Okay. So in this case, has no neighbors or even one like this one will die. Okay. If it had also 4 or 5 neighbors, sorry, what is that? Yeah, 4 or 5 or 6 neighbors will die as well. The next time I start, this will die. Only will stay on if it has 2 or 3. Okay. And if it is empty, it will get on if it has 3 neighbors. Okay. So summarizing, the rules are just 3 for birth. So if a cell is off and has 3 neighbors, will get on the next time. And if it is on, it has 2 or 3 survive, else will die. Okay, so that's the simple rule. Is that okay, or yeah? Yeah.
That's the rules.
That's the rule. Okay, I had to say this is because these are the microscopic rules. Okay, this is important. Well, okay, so this was discussed. What I'll tell in the next slides is based on these 2 books. Okay, the book of Derlekamp, Conway, and Richard, Winning Ways. You may know it. And this other one, which is a book for, you can read it. It's just a book for a book of to the general public by this philosopher called Damia, Darwin's Dangerous Idea, and also discuss these ideas somehow.
Yes, sorry, just to clarify. The birth, I mean, is it deterministic when a new one, I mean...
Is it completely deterministic?
So how do you find where the new is gonna come up?
So you get a given initial condition, a given configuration, then you simply count the neighbors. If it is on, if it is off, count the neighbors. You have 3, you put it on. Otherwise it stays another way around.
You go one place by one place, checking all the places in the network.
This is synchronous. You can see how this works if you want. Okay? We have some. This is the thing. So you put things. It looks like this. Okay. You can see already this is very complex. It's very difficult to guess what's going to happen next. Okay. So, well, typically you start from initial configuration, you get more or less a long transient, and you end up with something which is stationary or similar. Typically, okay? It could also expand. It's very unpredictable. Okay. So this is solid.
It's only 4 neighbors, right?
Sorry?
4 neighbors.
8 neighbors. You take also the corners. You take also the corners. 8 neighbors.
And if you change the rules,
So can you take
That's a different thing. That's a very important thing. I'll discuss later.
So
That's
the
a
rules
good
you have 4 or more neighbors, right?
Sorry?
4 or more you die.
Is
4
it
or more neighbors.
4 or more? You die of overpopulation. That's it. Okay. So, well, this is the kind of patterns you see. So you see very, very complex things. You see still patterns. So they are stationary. This is a block. Well, people has find a lot of these things, and they have put fancy names and so on. There's a lot of people, very, very smart people going playing with, and they have really, really amazing things. So there is a stationary patterns. There are oscillatory patterns with all sorts of periods. Period 2. This is period 3. Okay. And then there are, they call it the spaceships, things which are coherent and move a certain velocity with different structures, and many others. They put eaters, buffer trains, space racks, GANs. I can show you some for fun because it's really, really interesting to have a look at this thing. So I didn't know. You know this thing?
I programmed it back in late 80s.
Okay.
When I was a student at the
When he was young. And it used to be even a screensaver
So,
for Windows
yeah.
and Linux.
Yeah.
So let's say it's still live. There are really amazing stationary patterns. This, for instance.
And it's very easy to program in basic operator.
So this thing is stationary. Okay, it doesn't move. This one too. Somebody found this thing. So you run it, nothing. It's stationary. Okay. And then there are oscillators. Really fancy oscillators. This one, for instance. Okay, this is periodic. It runs like this forever. Okay, you can zoom in. You see these things happen, things colliding and moving on. Really complex. So this game of life really looks like life. So, really nice. I find it really amazing. So I didn't know all of this stuff going on. And many others, I'm sure you know. So people have to look around and find these things. And you know you didn't find these things on the book.
No, but the gliders and those ones that are...
Yeah, exactly. Well, those appear spontaneously. To find it, you have to look for this. And then there are spaceships. Or there are spaceships.
This is not true.
And those times, the gliders that were no
distance.
Yeah, but this is composed by many units.
This is computed by many units. Well, let's look at this.
It's independent units that you put together the battery work. So the battery
And the pattern is not.
no. The general pattern does not appear.
Look at this one. This one is not composed by
I don't know about the other one. But the other one, you have independent
Yeah,
units
this
which
is-
move,
that was it.
and then you place
That
them
was
to
the-
make the
yes,
pattern.
yes.
So the pattern doesn't appear because of the rules.
That's right. Well, there are.
No, porque los espacios se mueven, el forma que gira, puedes poner ahí y eso te va.
So, we have all these things, okay? Emerging. And this is an example of things emerging out of simple, okay? And that's this is related to your question. The game of life is a several automata, okay? But this is one of many several automata, okay? Essentially, what several automata is this thing. It's a game in a board. You have squares, and you have each cell can be on and off, and you have 8 neighbors into dimensions, okay? And then for such a you have 8 neighbors. Then you have, depending on the 9 cells, you have 2 to the 9 possible configurations, on and off, on and off, on and off, 2 to the power 9. So there are 512 configurations. And then the rule says out of the 512 possible configuration, if the next step will be on or off. Okay. So essentially, you have 2 to the power of 512 possible cellular automata rules in Turing. Okay, it's a huge thing. Well, if you want that the rule depends only on the number of cells that are on and off, and does not depend on the position, let's say, then this is 2 to the 18 lifelike rules. So these are all the possible rules you have. Okay. Well, then Steve Wolfram make a classification of these. Try to make this is qualitative classification of all the possible cellular automata depending on their behavior. Okay. In order of complexity. And he said there are class 1 cellular automata. This one, nearly all initial patterns evolve quickly into a stable, homogeneous state. Okay? And any perturbation disappears. So it's a stable thing. Class 2 cellular automata, nearly all initial patterns evolve quickly into stable or oscillating structures. So let's say this is a homogeneous stationary. Class 2 is oscillatory systems. Let's say perturbations in the initial pattern may filter out but remain local, so changes remain local, do not spread. Then there are class 3 cellular automatas. Nearly all initial patterns evolve into pseudo-random or chaotic. Okay? And let's say any perturbation, local changes of the initial pattern spread indefinitely. Okay, so you have essentially homogeneous stationary, oscillatory, and random chaotic, and spread out. And then very importantly, there is another class, which is class 4. We say that nearly all initial patterns evolve into structures that interact in a complex and interesting ways. So it's complex things. Okay? Well, they say class 2 type of stable oscillating structures may appear eventually. So you see oscillating patterns, but the number of steps required to reach the initial state may be very large. Even when the initial pattern is relatively simple. So you put a simple perturbation, and you see very complex thing that stays on for a long time, you may end up with a oscillatory thing. And importantly also, local changes may spread indefinitely. So may remain local, may spread, you don't know. Okay? So essentially this is something in the middle of 3 and 1 and 2, is something like being in a critical point. Okay? Perturbations do not grow nor decay, so you are sort of at a critical point. This is very important. Okay? And well, Wolfram has conjectured that many, if not all, class 4 cellular automata are capable of universal computation. Okay? So being at a critical point infer to the system very important properties. Okay? That's what I will discuss later. And this has been proved for rule 120 in 1D and for the game of life. I'll try to sketch the proof of this universality of the system. Well, this criticality gives to these systems very interesting properties. Okay, in particular the emergence of things. Okay, this is a discussion taken from this book, Darwin's Dangerous Idea. There are many special structures in the life world that emerge as recognizable objects at a new level. This guy called this a design level. The level has its own language, a transparent foreshortening of the tedious description one could give at a physical level. It is. You have a configuration like this one. To say the outcome of this configuration, you don't need to compute every time count. You have 8, not, and on, off. You don't need to do that. You know that this is a glider, this is an ether. You say that the ether will eat a glider in 4 generations. Okay? So you have this, the description, you can predict the behavior of the system at this level without going to the physical level. Okay? I show you a movie of this. Also, let's see if it works. This is a glider gun. Somebody find these gliders collide now and create a structure, which is a gun, you will see. This, every 30 generations, creates a glider. This stays on forever. So this is a glider gun. And then we can put an ether. Now you put an ether here. This guy eats all the gliders. And you can do these things without knowing the physical rules. You can play at this level. Very, very interesting. Very interesting. So something curious happens when you move between levels. At the physical level, there is no motion, just on and off. And the only individual thing that exists is a cell. That's at the physical level, defined by the spatial location. Where at the design level, we suddenly have the motion of persisting objects. It is one and the same thing. It is one and the same glider, through composed of each generation of different cells that move in diagonal, and there is one less glider when in the wall after it has eaten. Okay. And the salience is written on. Sorry, the salience of real things is considerable. One can ascend to the design level, adopt the catalog of objects, and proceed to predict the behavior of large configurations or systems of configurations without bothering to compute the physical level. That's a very interesting thing, which is showing this property of the emergence very well. For instance, one can design some interesting supersystems. This gives you a clue already of that big system that I showed you before, how they are built. Well, another property of this criticality is that the system is unpredictable. So the question is there some way to foretell the destiny of a life pattern? So, will it eventually fade away completely? Will it become static, oscillate, travel across the plane, whatever? Well, for instance, you put already a very simple starting configuration, straight line of n living cells. There is no way to give a rule. 5 cells will do that, 6 will do that, 7 will do that. This is the outcome of a straight line with the different numbers from 1 to 18. Some fade, this becomes a blinker, this case traffic lights at 6, this phase at 12, blah blah blah. I'll show you also a simulation of this. So these are lines with 2, 3, 4, 5, 6, 7, 8, 9, and 10. That fade, this one fades, this keeps oscillating, this is stationary. There's no rule. Well, it doesn't seem to be a rule. Okay. Well, there's a way to prove this, actually. There's a way to prove that this is really unpredictable. And the way to prove that is making a computer. Okay? Then you make a computer, every sufficient, well-stated mathematical problem can be reduced to a question of the predictability of life. Let's say you can do a computer, imagine you can do a computer in this game, you program any mathematical problem you want, and then this will stop or not. So saying if that problem has a solution is the same as saying if this game will stop or not. Okay? It's a very big question. Let's make a computer. So how do you do computer in the game of life? You need pulses to put bits in the system. So for that we take the gliders. We will have a 1, 1, 0, 1 string. You need a clock for a computer also. The clock can be a glider gun. Okay, so that gives you a clock. And then you need logic gates. And the logic gates can be implemented using possible interactions of these objects. Okay. We'll use the gliders to implement this. Well, gliders can collide in many different ways, depending on the angles they collide on. There are many outputs. Here they become a blinker. Here they become a block, something else. The very interesting reactions are the vanishing reactions, where they collide and lead to nothing. I can show you also a movie of some interactions. This is a whole catalog of interactions. Maybe this here, two glider collisions. Okay. These all these possible angles. I'll zoom in. Some of these ones, for instance. This will give nothing, this will give green or dark green. I'll make it slower or what you can see after. So you see those collides and give nothing, those will give something else, things like that. Okay, so you get this vanishing reaction, and then you can do things like an AND gate. You have a glider gun. This is your input, your string of input bits, 0, 1, 0, 1, 0, 1, and then you put this, you place this properly, such that here you have a vanishing reaction. If you have this one, a 1 colliding with a glider, it gets nothing. It does, and if you get a 0, this just goes through. With that, you got an inverted here. You have here inverted this string of bits. Where you had a 0, you have a 1, and so on. There's a vanishing reaction. So this is your string of bits, okay? And here you get a continuous string of gliders, 1, 1, 1. So you have a 1 will collide and will destroy. So you will get a 0. Instead, if you have a 0 right, so nothing, this will go through and you'll have a 1. So you have inverted the bit string of bits. It's an OR gate, right? You can do the same. You can make an AND gate. You can make an OR gate. This is the AND. Essentially, you get a glider gun, and you have 2 strings of bits arriving. Okay. Then here you get let's say you get a 1 here, and arriving here you get nothing. And when you arrive here, you have a 1. You go through. Okay. Then you get exactly. So you need a 1 and a 1 for this to get through and get a 1 here. And this makes an AND gate.
A 0 was 1 dot.
Sorry?
A 0 was 1 dot.
No, a 0 is nothing. Dot is nothing. Dot dies. So an empty space is 0.
1 is 1 dot.
And a glider is a 1. And if you just think of this using the vanishing reaction, you can build this AND. And if you do that, these are GANs. If you do this thing, you get that an OR gate. An OR and an OR gate. So essentially, you have these 3 basic gates. You have a full logical functionality. With these 3 logic gates, you can do any operation.
What is E?
Sorry?
In graph A, what is E?
This thing?
No. E left. So if output is A,
that's a meter. That all the stream of beams, the stream of gliders that goes here, you read them. Just
so it doesn't represent any logical operation.
No. Just if you build the gate and you don't want gliders flying around, so you just need them. So you need these under control. So exactly. Well, then you need, when you have this, you can build a universal machine. But you need a number of other building blocks. You need a keep-up reaction, you need auxiliary storage, you need thinning and glider stream if they are 2 parts, things like that. These are practical issues. But then you have these blocks, and you are a good engineer, you can ensemble them and make a computer. Actually, somebody has done that. It's amazing. This guy, Paul Rendell, has a web page. You go there, this guy in the game of life has built a universal machine. Universal Turing machine looks like this. It's a really amazing object. I'll show you a movie. I'll show you an actual simulation. This is amazing. But this is for this guy keeps working on this and has been improving the universal machine. And this is from March. So a couple of months ago, he put this in the web page. And you go. Sorry?
It's a virtual machine.
Is that?
Virtual. No, you say he has made it, but
well, no, in the game of life. In the game of life. So this is running in a computer. Okay. It's a parable of what the engines can do. Look at this. You make it run. Well, this is a very complex object. A Turing machine, well, I have not explained a Turing machine, okay, never mind, it's a computer. Essentially, you send a stream of bits that program the machine, and then you send another stream of bits which is processed by the machine, okay? This long string here is the thing to programming this. And then there will be another stream of bits coming on, and that will make some computation. I don't know how this works, okay? I have no time to go through this. It looks like this. This is birthday, okay? So this, you zoom in. Looks like this. So these are, you have all sorts of NOT gates, AND gates, glider guns, and things combining in such a way that this process comes.
But you need a programming language.
Sorry?
You need a programming language.
Of course, you need that, I guess.
The program is a set of zeros of 1 and
It's documented in the book. Yes, yes.
You want to do 2 plus 2, Victor, you want to do.
Yes. So you have yeah, exactly. Well, it's a Turing machine. It's not. So you don't program 2 plus, which is a Turing machine. This has, I think, 13 states. So a Turing machine works slightly different. Okay. So it has a number of states, and depending on the state, and you receive a 1, do something on the next bit, things like that, and you do the process. It's not typical computer. It's not typical logic. Okay, but nevertheless. So it looks like this. This keeps going on forever. It's a stable thing, and process things and you send them forever. Okay. Look at this. But I think these are memories. Or yeah. And here there is something, I don't know this what is for, but these arms here, they usually mean.
Are you injecting data right now? Or
so
is this the stable state, or are you injecting data right now?
It is injecting data. But these ones, it needs, we have here 1,000 generations. Need 1,019,000 generations to make a step. It sounds extremely low. It's like my computer almost. So here that is this is the stream of bits coming in. So you see here, you zoom in. These dots here are actually gliders.
It's a 1, right?
Exactly. You see? These guys are coming in. Somewhere. It's really huge. And here there is one arriving. You see this right here. So this is arriving. And then do something. I don't know what it is. As I will say, this is a program. So like this, essentially what you have done is you take the object.
What is the output?
Well, this is the charge of the program. So there's no output. You have to wait for all these things to go in, and you have programmed your universal machine, and then you will send another string of bits, and we'll process something, and then the output will come out this way. So this will be the tape of a Turing machine, and you have the tape coming in, and the result comes out. Okay, well, exactly. Again, this is the idea. Is this one that you have from the emergent, so these structures that emerge in the game of life allow you to do something at this level, design level. Okay? This is the emergence, and then how this level can do things that have nothing to do with the physical laws. Okay? This is very nice. This illustrates on how you can think of this like biology. Okay? So you have physics law, you have the laws of physics at the background, but there are structures that emerge, and then how these structures work have nothing to do with the physical laws, have another set of rules, which are these rules that allow you to do these things. Okay? You can think of, here of course there is somebody has designed this structure, but you can think as evolution and natural selection doing vitro. Okay? At the design level is selecting the structures that do things, actually that self-replicate, and the one that self-replicate better stay at that level. So it's a very nice thing. Okay, so this is the introduction. I'll go much faster now. Yeah, one more thing about the predictability. So you can program the machine in such a way that it finds a solution for a program, it destroys itself and stops. Okay? You can do that. It's amazing. And that, well, since mathematical logicians have proved that there is no technique which guarantees to tell when an arbitrary arithmetical problem has a solution, there is no technique that guarantees that the life configuration will fade away completely. So actually you have proof that this game is unpredictable. You cannot say an arbitrary initial configuration, it will fade away or will stay on forever. So that's a true proof of this game. So life is universal in this sense, has universal probabilities. Remember, I recall that this comes from that this game is sort of a critical state. So that's very important. Okay. So let me introduce you now the game of life. This is an optical system now. Okay? It's a big jump here, but you'll see my point. So you have this is an optical thing. You have a ring cavity with a nonlinear self-focusing beam, and you pump here a broad laser beam. You get some. But you can describe this with the envelope of the electric field. So this is the electric field. You have the envelope, and this is the z direction. The evolution of the transverse plane is described by this equation. So partial differential equation. You have time evolution. That's the losses to the mirror. The tuning between the frequency of the input and the frequency of the cavity, diffraction, the input, the nonlinearity, blah, blah, blah. Okay. If you think of this as a game, you put this in a computer, you make a grid, and you put here that's your grid, and then you compute the field at the position ij at time t plus delta t. Now our game is not a discrete, it's not on and off, it's a complex value, takes continuous values. Okay. At each time step, what you do is replace the value of the electric field there by this. You take a function of the value at the same point, this, the nonlinearity, plus this, and then a combination of the neighbors. Okay, I took here, I discretized the Laplacian. Simply find the difference. Okay, you can do more complex things, but whatever. So, what is this game? Which are the typical patterns of this game? You see something like this. This is changing the input power, easy. Okay. You can think of the input power as changing the rules here. Okay? Now, because before the rules were discrete, because it was a discrete game, now here the rules is changing the parameters. You change parameters, you change the rules. For high values of the input beam, you have things that are chaotic. This is a slow again, the machine. Well, exactly. Did you have chaotic patterns, and you put perturbation grow and spread all over the system. This is moving or looks. Okay, it's unpredictable. It's chaotic. Simply like that. If you perturb, the perturbation will grow and move over the space. For intermediate values, you have oscillating things, oscillating patterns like this one. I'll show you also. So these are simulations of the. These are oscillating patterns.
That's what you showed in near field or far field?
This is near field.
Yeah.
Simply you have pattern, bright spots oscillating and so on. Is it organized or chaotic? Okay. This is a stationary, okay? And then you go to the left for low pumps, everything it goes to the homogeneous system. So if we have an analogy, essentially this system for low values is class 1, for large values is class 3, in the middle something class 2 oscillatory. But there is a region, somewhere here where this is subcritical, that the system is sort of at a critical point. It's sort of clash point. Very, very much like the game of life. For this parameter region you have a lot of structures, okay? A lot of combination of structures. In particular, very important, you have a soliton, which is a single spot, which is right spot, which is a stationary. This is an emergent thing, like a glider, and has its own dynamics. Let's see how this behaves at the design level. I'm complicating a little bit because we want to make, I'm advancing, we want to make logic gates. So now we have our cavity, and now we are introducing here addressing beams to control the position where these spots will be. Okay, some control to make the casement and everything. So when you do this, the bifurcational structure of the localized state is you have a stationary solution, which is the fundamental solution. It has a smaller spot because of the dressing beam, and this has a unique bifurcation. And here you have a stationary localized state, and it has a hope and oscillates. And actually, the full scenario looks like this. If you go to the right here, it is oscillating. Here is stationary, here is oscillating too, and in the middle you have excitability. Excitability means that you start from here and you put a perturbation above this barrier, it makes a whole turn and goes back. So you move this loop. What I'm showing you here is the dynamics of a soliton in the design level, at the design level. Okay? I don't care about line now. I'm just studying the property of a soliton. So the perturbation is off, it will be on, so system is sitting here. Perturbation will be on for some time until the system jumps here, and then it's off, and you will see the response of the system. It's on, now it's off, but still the system makes a long excursion, goes back, and not also emit waves. So that's the behavior of the design level. Well, technically, this excitability comes through a bifurcation which is called saddle node in the circle, unique bifurcation. If you are in the oscillatory regime, you have a cycle, and as you move close to the bifurcation, the period diverge. At some point, you get a stable and unstable point that is created on the cycle, on the circle, and then you get this configuration which is excited. Okay? So that's a unique bifurcation. So this is, let's say, the mathematical reason that gives this property to these guys. Has some scaling, we have characterized that quantitatively. These are the modes of the system projected on this of the phase space projected on this plane here, and you see the snake bifurcation here. Well, there is full scenario. I will not go into it. I'll make another scenario on another day, more serious maybe than this one, where I explain there are deep reasons for this behavior in the system. But I'll just leave it for now. And then, well, we have these objects, localized states, which are excitable, and that's your behavior at the design level. And then we can do something similar what we did with the game of life. You can do logical operations using cavity solitons. By coupling excitable cavity solitons, it is possible to realize logical operations. So that's what I'll show next. I'll take these guys, and depending on how they interact, very much like the gliders, I'll make some operations. I'll make the NOR, and an AND, and an OR here. How you do that? So you put three excitable localized states there, and then you put them close enough. You receive a 1 here, a pulse goes into the input port, it jumps, fires, and then because of the interaction, very important, that waves that you're so propagating, this interaction may excite this one. Okay, this is set up in such a way that this interaction here makes this firing. So you got an OR gate. You put a 1, you get a 1. You put the reverse, you get the same. This is a 3D rendering of the world operating. You can see here the waves. So this is, you receive a 1, this fires. When it goes down, emits a wave, the interaction makes this fire, so you got a 1.
So the center soliton is the
output,
and
correct.
The left and right are the inputs.
Correct. Very well. That is the thing. So you have the input and the output in the middle.
So if you have two ones, they annihilate each each other?
No, you have to one. You get this is not okay. You get the same thing. So the two fire, the two make this fire. That's it. So it's an OR game. This is the two ones. Okay. You have two ones and the fires. You can make an AND now. To do that, what you do? You want now that in an AND, if there is a 1 and a 0, you need 0. So what you do is just load the threshold of excitability of the middle, such that a firing of a single input is not enough. You need both to fire to switch on to make the middle one to respond. So you move out this. These are all the movies of Adriano. Oh, great. You cannot see we can make a good try or something.
Manda solo alla pantalla.
That's what I'm not doing. There you go. That's what you receive for 1. This fires. Nothing happens as an AND. So 1, 0, you get a 0. Nothing is really. Okay. We go to the next. Okay. Now you receive a 1 and a 1 at the input. And now, let's say you have twice the perturbation in the middle. That's enough to make this one fire. 100 something. This goes up. This goes away from the fixed point and fires. You got an AND gate. Okay.
Compared to the previous case, they were further away, or?
No, well, you can do that. You can keep the parameters fixed and put them farther away, or you can decrease the excitable threshold. That you can play with that.
So the time takes could be different, right?
Yes. Yeah, that's right. Well, and then here the important parameter is interaction, and the parameters are the distance and the thresholds. But you can play with geometry. This is 2D, and well, that was in a straight line. You can put here in a triangular manner. It's the same thing. And here you could think of using this one as the input for an X gate and make computation in the transverse plane going down, for instance, and make several gates one after the other. Yes.
Could you use interference of the coupling? Use different distances so you don't get the different reaction times? But
Maybe either. It's very. I mean, Adriano had to, let's say, tweak this a lot to make this work. So what you're saying is that just playing with the interference, you may need, yeah, exactly. So constructive thing that excites or it's very complicated. We don't know. Okay, so we have the AND, and we still need the NOT to make full logical, complete logic functionality. For the NOT is a gate that you need only one input and one output, and you want that it gives ones when you send nothing. So for that we use the soliton in the oscillatory regime. So you get nothing, you get ones. And when you receive an input, that we have to reverse the phase here now. This sets the cavity soliton below the oscillatory threshold. You skip one oscillation when you receive an input. So this can create an inverter. Well, and that's it. So we got all the three basic logic gates. So we have full complete logic functionality. So in principle, you could make a computer with these things. Okay? Similar with the shown for the game of life.
You could do it with any excitable system.
Sorry?
You could do that with any excitable
That's
system.
right. That's right.
What I don't get, where's the link to the game of life?
Sorry?
Where's the link to the game of life? Because what you show here, the logic operations have nothing to do with the logic operations.
Absolutely. Absolutely. The link is that we are using emergent structures. Okay? And we were designing this, so we are creating this computation at the design level. So independent of the physical rules. That's the analogy. So this is live here now, but this could be.
But you haven't, for example, checked whether you could realize some kind of game of life with in this configuration, because at least for these logical operations you have, could you generate physical game of life?
I mean, if it has full logical functionality, you could do that. You could program.
No, the logical functionality has nothing to do with the game of life.
Yes. Well, you could program.
You can program the game of life.
That would be again a third meta.
Yeah. No, what you mean is that if one can generate gliders and these sort of structures in this system similar to that.
No, whether you can create the rules of the game of life. I don't know. Because the very particular rules of game of life only make it perform in that way. And if you vary the rules to it, it loses all the
You see, you are thinking not typical implementation of the game of life, not here. That's not the intention. So the idea is this one of computing as a designer. Okay. And yeah, okay. So
the nodes, how is it again? How do you implement the nodes?
you have the system in the oscillatory regime.
But you have to change the parameters.
You need, but you have.
Every pod has a different.
This is not exactly as it's not exactly as the game of life. Okay, so here you have to design something here. So you have these addressing pins for the gates. The picture. Here, to create the gates, you have to design the gates on top of the system. Okay, not create them as initial condition only, but it has to be applied always. And so the value of the parameters of the addressing pins sets the properties of the gate. So if we're changing that slightly, you can make an or an OR gate. Okay. So it's not exactly as it's not as universal as the game of life in this sense. But just exactly. Okay. Well, you may ask. Well, you have shown this system, optical system, that is excitable, but is that general? Well, it is not. Typically, well, many systems have localized states, these solitons, but not all are excitable. So in that sense, it's not that any system displaying localized states can compute. But there is a trick, though. And the trick is, which are the ingredients to have this computational capability as I have shown? You need excitability. And the minimum ingredient is a stable fixed point, which is the homogeneous solution, or the small band, a threshold. That's intrinsic for any cavity soliton, for any dissipative soliton, because that you always have this middle branch that is a separative, so you always have a threshold. The tricky thing is the reinjection mechanism in phase space. In the case I've shown, which is the Jacobi-Lefebvre equation, that's intrinsic. There are some reasons for that. I'll talk another day about that. But in general, you don't have that. In general, you have a bifurcation diagram like this. When you have a defect, you have the homogeneous solution, and if you go beyond this, it switches on and stays unstable. That's a localized structure. Has no excitability. The trick is if you put a defect plus a drift, and this is discussed in these papers, although they don't talk of excitability, but it is. When you put a drift, what happens is that you have a defect and creates a localized state. The drift takes the localized state away. Okay, and that essentially gives you excitable system. Where you have a point here plus a drift, and you excite it, create a bright spot, and the bright spot detach and travels away. And this system has a sneak bifurcation, very much like the one I showed before, and this system is excitable. Excitable in the very same manner. So this is the oscillatory regime. So this is before the sneak, and this is oscillating and creating a spring of solitons. Okay. That would be they call it a soliton tau. That would be lighter than if you want picture that creates localized states. This is a buffer memory or a shift register. But the idea is that with this trick of putting defects and drift, you can make any system having localized states excitable, and you can combine these excitable units to make computation. Okay, so the message, I'll skip that. So the take-home message is that systems displaying dissipative solitons are universal. Very much like the game of life. Okay, so you can compute at that center. Okay. And well, I'll go back once. This is very. I presented this as a theoretical thing, very a basic question about universality computation of complex systems. But there are some practical applications, and it is in optical computing. There have been a lot of discussion recently in Nature Photonics on articles that claim that this is an important step to avoid some limitations of electronics. So there is some interest in having computations all optical. On the other hand, there is cavity solitons have been suggested for that as being able to compute, or not compute, sorry. They were suggested to store, as a memories to store information. There are some papers where this is an all-optical delay line using semiconductor cavity solitons, and this is, well, it's in temporal domain, but it's very much the same. It's a memory, an optical memory with 45 kilobyte capacity at 25 gigabits per second. That's a memory using cavity solitons. And we suggest that you have these building blocks, memories, and you use this excitability. You could make a small computing devices all optical. So it has some technological application, although very specific, I must say. Okay, again, that's the take-home message. Thank you for your attention.
Just to coming back to your before last slide with what you say is drift and the defect gives you excitability. I'm not sure whether that argument holds, because in the end all what you do is you create convective instability, and you have simply if you make a parameter transformation or coordinate transformation, you would have
I didn't say it.
If you would take the coordinates you want to use, which are local ones, you would completely lose the whole area, because you always have the rest needing for the exciton for the excited solitons.
Yeah, well, there are two things here. One is since you have a defect, you cannot make that transformation because you have broken the rotational system. So actually, you cannot make that. So it is in this sense excited. But you cannot.
But that's only for the process of exciting it.
With the draft, you need a defect plus a drift.
Yeah.
In a big system that is not excitable in the sense that this stays forever. The point is that you have a boundary always, and it dies, and then essentially you go back to the region.
And it's a convective instability. No?
It is related, but so let's say you have your initial configuration in your system with boundaries and has a bump here. Okay, now you perturb this, and this will switch on. This will switch on, and then decay and move away, and it will die out. And in the end, you will go back here.
Yeah.
So globally, the system is excitable. So you have a long excursion, and systems go back to the same. That's a reinjection mechanism. You have a defect plus a drift.
Where's the reinjection?
Well, this dies away, and you go back to the same original. You go to the same original mechanism. In phase space, you think globally, in the phase space of the whole system, what you've done is you were at a fixed point. There was a barrier. You excite.
That's a bit of a trick with boundary conditions here.
Yes, of course, globally. Yeah, yes.
No, I mean, the fact that what you need is defect plus drift plus boundary plus an absorbing boundary.
Yeah. In an infinite system, the reinjection mechanism is not such, because this stays forever. So actually, you can change a different state, but that cannot go forever anyway. So it has to die somewhere. When it dies, you go back to the same state. But it works. We are trying out. We have the idea. We have not started, but we want to do this in the Swift-Hawking method. If we succeed, we will prove that the Swift-Hawking method is a very general amplitude equation for a Turing atom-forming amplification that applies to fluids, to many systems.
Is that a smart operating regime to work in? Because in the end it means you lose your whole plane that you can address, so the whole spatial extension that you want to use here or benefit from, because you don't want to create only a single logical gate, would completely destroyed by the fact that you have to reserve all the
you have to avoid
moving
you have to avoid the stream of things going out. Yeah.
Or you can use this to build, as in the case of the
You could, yes, you could use that as a memory. Yes. Just a fun building.
For neuroscience interested people, that's both of you, this thing of the drift and so on in the end is very similar conceptually to the integrate fire kind of models. I mean, you have and when you arrive to some point, then you reinject, and you also have get some effective excitability.
Well, but here you create the reinjection only when you say, okay, I have boundary conditions where it disappears.
Okay, but I mean, the idea is the same as the
which is true of any system that I know. Do you know any that does not have boundary conditions?
No, the integrated fire model doesn't have spatial.
That's a model. That's a model. That's not a physical system.
That's a level of things.
I don't know any physical system that doesn't have a boundary.
There are physical systems.
That does not have a boundary.
Well, it doesn't have to be a spatial.
I mean, if you have a system that it has dissipation of an absorbing boundary, that trick will work.
Anyway,
Even if it does not have, even if it does not have dissipative boundary, and it will have very large, and it has some absorption.
I mean, locally you could use these properties.
Anyway,
but you pay a high price.
Oh, yeah, that's true. But yeah, you pay a price, but you can install.
And so you go from 2D to 1D.
Yeah.
You can only use a slide. You still could.
I never understood the blah 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 of criticality in this kind of thing. I mean, in the game of life, Wolfram says about some critical state. Basically, he just means that is neither too random, neither too ordered. This is the only meaning. And then you use the word critical in a sense which I don't understand, but essentially you say it's bi-stable, so it's something I never will call. I will never call critical. So could you explain which sense anything of this is critical?
It was an abuse of language, if you like. Yeah. But
do you think in any way you need something critical?
The first thing, this special property, you need this localized states, stationary, and so on. You have to be between two boundaries where you have a stationary front and so on. And all of this happens, interestingly enough, close to a typical point
in this model. For example,
in every model.
In the computer you have on the table, the transistors are bi-stable. I don't know. I don't know in which sense something critical is needed to build a computer.
No, not to build a computer. To build a computer
or
with
to build a gate.
To get an emergent properties. But what I'm saying is that you have a system that has nothing in principle. Maybe you cannot compute in this sense. But if this is a critical state and has emergent properties,
I mean,
at that design level, that's what I want. So
can you rephrase? If you have a system which has emergent properties, you can compute.
Correct.
What is the critical work needed?
You need for the emergence, you need to be close to the critical. You need to be at the critical.
I don't believe that. Well, I don't believe you can define critical by this.
You can define critical by this. Yes. But for instance, in the game of life, if you think of the room as a perimeter, you are somehow at the critical point or close to the critical point.
Are you going to change the room configuration?
No, of course not. This is we can discuss for hours here. This is a philosophical thing, and the proper description of critical. I don't want to go into that. But here it happens similar as I showed before. You think of this as changing the rules. You need to be close to, more specifically, you need to be close to this bifurcation thing, and this has to be from subcritical to super to subcritical. So there is a very specific coordination to a point where all these things are shown emerge. So what I'm showing today for these systems, say for computing with having solitons, you need to be close to that critical point. If you go somewhere far away from that, you cannot do it. In this sense, you need to be in a critical state or close to critical state. Okay, that's blah.
So
I was very I was very fascinated and like that a lot that you say you want to make use of emergent properties for computation. And at one stage I was extremely disappointed. And it is the emergent property is an immense computational power because you have the self-organization of the system. You may say some kind of internal computation that the system does, the dynamical system does itself, that you want to benefit from. And you have all these kind of mechanisms contributing, for example, to the dynamics of such a soliton, that you have the possibility, as we show here, to arrange them in patterns, have them interact. And all these huge internal computation that you have for this, you castrate it completely by reducing it to a binary logical gate that you want to implement there. And at that point, where you go from that, you say you want to use the emergent properties of the system, which have an immense computational power, and then say, but afterwards, and now because that's the way how people build computer, I realize logical gate. I think it's an incredible waste of computational power.
That's correct. That's correct. You may think of rest of a computer.
I was not thinking. I didn't. No. Don't get me wrong. I don't want to make a point because that is only one very specific thing. But what I'm thinking of is whether one can, in this very configuration, not make much smarter use of the emerging properties in order to perform computation. Why going back to logical gates?
Yeah, you're probably right. There may be other strategies that I have not explored, so that we have not explored, that may be used to compute somehow. I don't know. We simply stay at this level because it's the simplest, and because proving this somehow proves universality. So we stop here. We are not planning to go much farther with this. Okay?
That's a bad idea.
Huh? Yeah, we can discuss that. You can decide. I don't know, but the idea is this one that, yeah, exactly. You can use these emergent properties again, and well, you don't need to integrate the whole non-linear Schrodinger equation to make the gates and so on. You can plan the gates and then do the max computation is done by the system.
Because the question would be, how can you most efficiently make use of the emergent properties that you have, for example, here in this solitonic system?
I have not think of any other way. You have any idea? So, I mean, reservoir computing would be a straightforward thing. Although reservoir computing is for specific tasks, it's not universal.
But I would not see how one would immediately map
it. It is
universal.
In principle, the system would have that too. I don't know, you think properly how to interpret the states and whatever. But I'm not thinking of that.
It would be interesting, I think.
So, any other questions? That's not the case, but thanks.
Wow.